let's say that the limit put-off function is positive, but the derivative is also positive. Change that, sorry, I'll fix that in the notes. Then it's unstable. Right? And did I get this one right? Yes. If it starts off at 0, okay, my limit put-off function is negative, and the derivative is also negative, the system is unstable. Right? So all the criteria fit for a limit put-off function for stability. Any of those things change, I have an instability. Okay. Let's look at the case for a linear time invariant system, which is mostly what we'll talk about in this class. Linear differential equations, nothing changing over time. If I have all numbers, it's pretty trivial. Right? I just look at the A matrix, right, which is basically the differential equation for the system. And all I have to do is make sure that the eigenvalues of the A matrix have negative real parts. Done. If I have all numbers. But if I don't have numbers, then I have to look at some things here. Right? So if I have a totally numeric system, I'll just look at the eigenvalues and no one's stable enough. But let's assume we don't necessarily know what they are, or not necessarily all numbers. I can define a limit put-off function as some R matrix x transpose x. Really what I'm doing here is some R x squared. It's the state squared. Realize that that's a form of some constant times x squared. Right? Followed by that from your linear algebra. All right. And if R is some positive definite matrix, what does that mean, positive definite? One thing to determine it is non-zero and positive. Right? There's ways of determining those things. Right? And if we look at the derivative, we'll take the derivative of this thing. Okay? Derivative of x, or v, is x dot Rx plus x R x dot. Right? R is a set of constants. That's derivative 0 for that. But space between them works fine. So differentiate that times Rx, x transpose R, and derivative x. Okay? Problems with that? Okay, so then we put in the state equations, same as we did before. So every time I saw x dot, well, x dot transpose is A transpose R. Let's remember some linear algebra here. And I'm looking at this part of it. Okay? So I'm saying x dot is that. X dot transpose is what? It transposes this. What's that equal to? X transpose A transpose. I'm going to reverse things here. So I need to do that. That's why we get A transpose R or A. So, okay? Stop. Now, for this thing to be, we want the derivative to do what? We want it to be what? Negative. In fact, negative, definite. So, I'll call this, that mess in the middle, Q. Q is this A minus A transpose R plus A, or A. And we want that to be a negative definite. So, what we do is, typo there, I choose an Q, which is symmetric, positive definite, or at least semi-definite. Right? These solve for R. R can be symmetric, not hard. And we use Sylvester's theorem to make R or check that R is positive definite. Did you ever go through Sylvester's method for determining positive definiteness in a class? No, it's not too hard. Well, let's go through it. Okay. So I want this this thing to be positive definite, and what you do is you look at all the various submatrices of R. That the first submatrix, which is just coefficient R11, must be greater than 0. This whole determinant of the next one must be greater than 0. The next submatrix must be 0, next one, next one, next, until the whole thing is checked for 0. That's Sylvester's method for checking for positive definiteness. Yeah?
What's the R?
That's the matrix we're going to be matrix of coefficients for our Lyapunov function. So in the energy problem, all right, R was like, what is it, 1 over M, 1 over K vectors. Okay? So it's some matrix that we're using for a Lyapunov function. But Sylvester's theorem says you can check for positive definiteness if you go through this procedure of checking each, expanding out 1 by 1, 2 by 2, 3 by 3, 4 by 4, whatever. Check each one of those to be determined to be positive. Right? Then it's positive definite. Okay. If any of the determinants is 0, then it's semi-definite. Okay. Let's take an example. There's all symbolic. Right? And it's supposed to be a 1 down there, not a 10. And I'll choose some Q matrix. It's an arbitrary thing. I chose it to be symmetric, and I said, well, I'm going to make the diagonal 0, 2, 0. Right? And that's a candidate function to see if I can show definiteness here. All right, I know Q must be A transpose R minus R times A. Right? Drive that before. That's to get the derivative of the Lyapunov function. So take the transpose of A times R. I know what the coefficients are. Right? Times R times A. And I know that must be equal to Q, which is 0, 2, 0 on the diagonal. And multiply it out and solve for all the R's. All right, so this is what I get for the R matrix. Do that. All right. So taking all the functions of this thing. So set Q to be my desired value, and it basically solve for the R's. Now, I want to say, use Sylvester's theorem to check on positive definiteness. It says the first coefficient, AC over AD minus C, must be positive. The next determinant, which is AC, A squared plus B over AB minus C, must be greater than 0. Then that full matrix determinant must be greater than 0, and my projector is cutting that off. So Sylvester's theorem, to prove that R is positive definite, must satisfy all of those things. Okay.
I have a question.
Yeah.
Aren't we checking for positive definite just if we're taking the derivative of the whole matrix anyway?
You can get that, but you can have submatrices that are negative, which means it might be overall positive, but not positive definite. The determinant is positive, but not necessarily positive definite. Very subtle distinction between those. Right? We'll solve for A, B, C on those, and you get A must be greater than 0, C must be greater than, and AB minus C must be greater than. In fact, if you did the Routh-Hurwitz, you get exactly the same answer for this. Right? Because it's a linear system, we couldn't use Routh-Hurwitz. Right? That's the procedure. I only do that procedure if I have some variable, non-numeric variable. If it's all numeric, I simply get map that and look at the eigenvalues. Right? Way simple. Now, you can do some nice nonlinear things here, though. So here's the problem. Right? X1 dot is equal to X2. X2 dot is equal to this nonlinear function, X2 squared minus X1 cubed. All right? And I can kind of rewrite that in terms of X1, X2, but not B2. And I want to try to find some Euclid function that will show me stability of the system. So what I'll do is let's try X1 squared plus X2 squared. All right? And this is where it gets hard. I have to find some Euclid function that will satisfy everything. All right? So this is kind of like energy. Yeah, no problem. This is kind of like potential energy, kinetic energy. Maybe that might work. It satisfies the condition that for X1, 0, and X2, 0, it's 0 for all time. Right? Is it positive for all time? No matter what X1 and X2 are? Certainly. Satisfies that. Derivative of it. And do that, put in the state equations. Right? It's indefinite though. So I took the derivative of this, put in the state equations for it, what x1 dot, x2 dot are, and I get this thing, which is x1, x2, not necessarily the best thing, x2 cubed. You know, that could be, this is not necessarily negative at all times, and x2, x1 squared. You know, this way. So I have indefinite sort of result here. Yeah?
Just quick, even though when you do x1 plus x2, if x1 and x2 are both 0, that still doesn't satisfy the second.
This is satisfied for 0.
Well, like, is it the second task of it?
All right, for any non-zero states, for any time, is it possible? Yes, all is possible, so it satisfies that. But our derivative is kind of indefinite. It doesn't really show that we have definite regions of this being negative. So you might try some other Lyapunov function. And you notice we have one x1 squared here, x1, or x2 squared, x3 cubed. I might try something of x1 to the fourth, because then when I take the derivative, I'm getting x1 cubed. That might work nicely. Yes?
When you say try, like, how are you finding these equations? Or
I am trying out what's...
just
That's the hard part. It's you trying to figure out a Lyapunov function. I usually start off with something like energy, like x1 squared plus an x2 squared plus x3 squared and so forth. Right? If things don't work out, you start trying to find a pattern. You say, well, look at these cubics coming up here. Can I get rid of all these cubic powers? Those are indefinite. Right? I want even powers of all my states on the derivatives. That means it's very definitely positive or negative for no matter what the state is. Right? So these cubes and x1 times x2s are things I don't like. Yeah?
Do we try to pick convex functions for these?
Yeah, we are. Because I want to so, here, here's our Lyapunov function. Satisfies that x1 is 0, x2 is 0, it's 0. For any value of x1, x2 positive, take the derivative. Well, derivative, put in the state equations, get rid of x1 dots, x2 dots. I get this, and it's getting close. Oh, that one's nice. Right? So I've got a cube here, and a cubic there. All right? What you might try is you look at this thing. I have a x1 cubed, x2, x1 cubed, x2, minus 2 and minus 4 here. What if I could get these two canceled? Right? I'm going to try to cancel those last two terms. Okay? And the way to do that is try this. 1/4 2x2 squared. All right? Satisfies that. Ah, look at this derivative now. I said cubic there, but x1's disappeared. Right. So does that satisfy the conditions for all x1s? Yeah. So I have this x2 cubed, but when will that be negative? Okay, if x2 is positive. What I've done with this nonlinear function, nonlinear system, I found a region for stability. Right? And that region is what? I've shown that anything in that region is stable. I've shown it for entire space? No. I've shown it for the entire space. I've shown it for at least a region. And that's very typical of nonlinear systems. Right? There are regions of stability and regions of instability. Now, a linear system, if I've shown stability, is it stable for the entire space? And x1, x2 is the space. For a linear system, if I've shown stability, is it stable for the entire space? Any thoughts? So for any value of x1, x2 for a linear system, can it be stable? Well, think about this very simple mass spring damper system. And let it be all nice linear differential equations. We show that to be stable. Is that stable for all x1s and x2s? There's our candidate fluid constant. I did that one. Found the derivative of it, put it in, and we found that for any value of x1, x2, was it stable?
Only if B was positive.
Well, it'd be, so simply be the positive in this guy. So, nice viscous damping, B is positive, K is positive, M is positive. Was it stable for the entire x1, x2 space?
Yes.
Yes. And that's the nature of a linear system. Linear systems are either stable or unstable, and it's the entire space. That's not true of a nonlinear system. Right? Nonlinear systems can have regions of stability. Right? Example. A pendulum. What are regions of stability and instability? Do you have that? What's that? No, I'm going to assume small. It's non-linear. Well, I know it's linear. I don't know what's non-linear.
The origin is stable.
Okay. Let's look at this. In fact, what's actually one in this case? The angle. Right? It's two, let's say, derivative of the angle. Shot. Here we are. One. Two. Right. If theta is equal to 0, x1 is equal to 0, is it stable? Here, here. Yeah. So right here, stable. Right. As theta gets up big, it gets up to 90 degrees, still stable?
Yeah.
Now let go back. Got 180. Is that a stable equilibrium or unstable?
No,
Unstable.
it's not safe.
Pi